In this video, we'll try to represent a system in controllable canonical form whose transfer function is given by this expression, where the numerator polynomial order m is 0 and denominator polynomial order is 3. So which means there is no numerator polynomial as such, only a constant. So the first procedure is to split this transfer function into two parts, where y of s over x1 of s times x1 of s over u of s. This can be written as 1 over 1 times 1 over s cube plus 9s square plus 23s plus 15, where y of s over x1 of s is associated to this expression 1 over 1 and x1 of s over u of s is associated with this expression. Now let us write the first expression, where y of s is equal to x1 of s. Because it is 1 over 1, it's 1, so y of s can be written as x1 of s. Now the second expression, where we can write u of s is equal to s cube plus 9s square plus 23s plus 15 times x1 of s. Now the first expression that we have here, where we can say in time domain y is equal to x1. Coming back to the second expression, we can write u of s is equal to s cube times x1 of s plus 9s squared times x1 of s plus 23s times x1 of s plus 15 times x1 of s. We can rewrite this expression in terms of time domain, where u is equal to x1 triple dot, because in time domain 3 times differentiation of x1 is in Laplace s cube times x1. So I'm writing x1 triple dot. So what I meant by this is x1 triple dot is equal to d cube over dt cube times x1 of t, okay, plus 9 times x1 double dot. Now x1 double dot is d square by dt square of x1 of t plus 23 times x1 dot, and x1 dot is a single differentiation with respect to time of x1 of t, plus we have 15 x1. Now we're going to define another variable, state variable x2, which is x1 dot, which means first differentiation with respect to time of x1 is x2, and we're defining x3 as x2 dot, which means I can say x3 is x2 dot, which is equal to x1 double dot. Now should we define x4? Of course not, because the order of the system that we have is 3, which means we can define 3 state variables. So that's why we did 3 state variables definition, x1, x2 and x3. Based on these assumptions or definitions, let me rewrite this expression that we have here, where u is equal to, I can write x3 dot plus 9 times x3 plus 23 times x2 plus 15 times x1. We have these 4 equations from the definition or derivation from the previous slide. We can rewrite this expression in terms of x3 dot as minus 15 x1 minus 23 x2 minus 9 x3 plus u. We're trying to represent them in the standard forms in state equation and output equation form, where we know they should be represented as x1 dot, x2 dot, x3 dot, which is a vector, is equal to the matrix A, which will be in 3 by 3 form, because the matrix A depends on the order of the system. So the order of the system we have is 3, so the dimensions of A will be 3 cross 3. And we have 3 state variables, x1, x2, x3. And we have the matrix B, which is 3 cross 1. And now we have the output expression, which can be written with x1, x2, x3 plus u. This is the state equation, this is the output equation. Now let us find the content of matrix A. We know x1 dot is equal to x2, which means we can put 1 here, which is corresponding to x2, and the rest of the terms 0, because it doesn't depend on u or x1 or x3. It depends only on x2. And similarly, x2 dot depends only on x3. So we have 0 here, and 1 here. Representing x2 dot is 0 times x1, 0 times x2, 1 times x3, plus 0 times u. And now for x3 dot, we have a lot of terms here. Let me put them. x3 dot depends on x1 with minus 15 magnitude, and here minus 23 with respect to x2, and minus 9 with respect to x3. And it depends on input u, so with magnitude 1. Now let us go to the output expression, which is y equals to x1. It's a simple equation, so it depends on x1. It doesn't depend on x2 or x3 directly, and it doesn't depend on input as well directly. So this is 0. Now let us represent these set of equations in terms of signal flow graph. We know the output expression, I'm saying y is equal to x1. So I'm taking a x1 node, magnitude is 1 because x1 is y and y is x1. Now we know x1 dot, if I take x1 dot here, which is nothing but x2, if we integrate x1 dot, we will get x1. So which means if we integrate x2, we get x1. So I'm putting an integrator whose transfer function is 1 over s. And similarly, if I take x2 dot and integrate, I'll get x2. So this node is x2 dot, this node, and if I integrate, I get x2. This x2 dot is nothing but x3, so I'm putting x3 here. Now another node x3 dot, x3 dot. If I integrate x3 dot, I get x3. So I'm representing this. We have 3 integrators representing the order of the system is 3. Now x3 dot depends on x1, x2, x3 and u. So let me represent that in signal flow graph. So if I take this is the input u, then 1 times u minus 15 times x1. So x1 is here. Let me take and feed it back, and minus 23 times x2. We have x2 here, so feed it back with minus 23, feed it back with minus 9. So we have this 3 feeding back, x1 feeding back with minus 15, x2 with minus 23, x3 with minus 9, and input also coming. In this special case where output was equal to a state variable and rest of the state variables are defined as derivatives of that state variable. So in this case, we can say all the state variables are phase variables. Phase variables are those particular state variables which are obtained from one of the system variables. In this case, the system variable is y, the output, and its derivatives. So in that case, we took y, the system output, as one variable, and we defined all other state variables as derivatives of them. So we can call this phase variable representation as well. So in most of the cases, people call this controllable canonical form with phase variable representation.